Welcome back to our deep learning web series, Comprehensive and Intuitive Introduction to Deep Learning. We are at episode 5 of season 2. And in today's episode, I'm going to talk about a novel neural network architecture where you can take two individual neural networks and then connect them together to solve some very interesting use cases. Let's dive in. It's called sequence to sequence models. Let's try to understand what problems they solve and why and how they work. So, before we get into sequence to sequence, let's do a quick recap of the type of neural network architectures we have studied so far in our web series. The first one we studied is called as a feed forward neural network. In a feed forward neural network, you have an input layer where you'd be essentially sending in input, and then you have an output layer at the other end where you'll be making the predictions. And then in between the input layer and the output layer, you have one or more hidden layers, and you would essentially pass the input signals from the input layer through the hidden layers to the output layer and make a prediction. And we saw several use cases that you could solve with a neural network architecture like this. Things like regression problems, where you're trying to predict the price of a house given attributes like the square footage, the bedrooms, lot size, and so on. We also saw that you can essentially do things like classification, whether it's binary classification or multi-class or multi-label classification. Then we studied another form of neural network architecture called recurrent neural network architecture. And we said that an RNN addresses the limitation of a feed forward neural network when the input is of a form which can be broken into a sequence of individual items. For example, if you take a text could be a sentence or a paragraph, but we know that a sentence is made up of individual words, and the order in which those words appear in the sentence can determine the meaning of that sentence. So you would want to have a neural network architecture that can take in an input, split it into individual components, and then understand the pattern and the context that is flowing across all these individual items in that sequence, and then make a prediction. You can use that for text. We can also use it for things like time series data. And we studied classic recurrent neural networks, classic RNN. And I also showed you another type of an RNN called LSTM, which is long short term memory. And I showed you that in a long short term memory, you would essentially be able to capture not just the short term context that is flowing across different words in a sentence, but also capture the long term, the memory that basically says whatever has happened earlier on in the sentence or earlier part of a sentence will influence the meaning that comes out at the end. So an LSTM essentially addresses that. Now, these are two very powerful neural network architectures. However, if you want to solve a problem like the following, you're given a sentence, and let's say the sentence is in English. It says, he quickly ran across the field. And you would like to build a neural network that can take this input or the source sentence and then convert it into a sentence in a different language. For example, you want to take an English sentence and then you want to convert it into Hindi or Telugu or Spanish and so on. So, what kind of a neural network architecture will allow us to do these kind of things? Can we use a feed forward neural network? Clearly, I told you that when it comes to text, a feed forward neural network doesn't work because it cannot capture the context that's flowing across different words in a sentence. Okay, then can we use an LSTM or an RNN? You cannot, because the reason you cannot is the LSTM or a recurrent neural network is very good at understanding the context that's flowing across the different words in your sentence. And it can be used to, for example, do classification of that sentence. Okay, is the sentence basically carrying a positive sentiment? Is that sentence carrying something that you want to classify as spam or not, and things like that, right? Or you can also use it to do the next token prediction. Given half a sentence, you can say, okay, complete the sentence by predicting the next set of tokens, which is great, which is what LSTMs and RNNs can do. But here we're talking about completely different things. What we're saying is we want to take a sentence, a full sentence in one language, and translate that into a sentence in a completely different language. And the source sentence by itself stands on its own. The target sentence in a different language stands on its own. And you really want to figure out a way in which you can do that translation. The source could be of one length. The target could be of a completely different length. For example, here I show you, he quickly ran across the field. In English, is only 6 tokens or 6 words. But when translated into Hindi, it basically becomes a sentence that has 7 words. Right? In another language called Telugu, it translates the same English sentence can translate into 4. In Spanish, it translates into 5. So you want a neural network architecture that can take a source of one length and convert it into a target of a different length. The other interesting observation here is if you notice the target sentence, the words do not have a one-to-one mapping with the source sentence words. For example, in English, he quickly ran across the field. the word field is the last token or the last word in the sentence. But in Hindi, the corresponding word for field, which is sixth in English, is actually Maidan, which is the fourth token in Hindi. Which means that this neural network architecture cannot just take a word in the source sentence and then generate a corresponding word in the target language. So this means that we need a neural network architecture that not just takes words that are coming in from the source sentence and then word for word converts it into the token in the target language. It doesn't work that way because, as we see here, field is sixth in English and Maidan is 4 in Hindi, right? So what would that neural network architecture look like? To be very honest, most software developers are not really excited about building neural networks that can translate from one human language to another. However, the same neural network architecture can be used to do human level language and translate it into machine understandable language. For example, if you think about the word CLI, what does it remind you? So far, whenever we hear the word CLI, it reminds us of command line interface. What if I tell you that we are now in an age where you can essentially take CLI, which is command line interface, and convert it into what I call as conversational language interface? So what is a conversational language interface? So in a conversational language interface, instead of the human or the operator or the DevOps engineer remembering all the nuances of different commands, they would be able to express their intent of the action that they would like to take on the system using plain English. And then you want the neural network to basically convert that into a command or a set of commands or an API call that will actually take that action. Let's illustrate this through an example. So let's say that the DevOps engineer says, hey, show me all files in this folder sorted by their size. We want a neural network architecture that basically understands what is being asked here, and then it emits a command like ls minus lh capital S, which will essentially give you all the files sorted by their size. Or something like, does this web page have anything to do with deep learning? And then the neural network architect automatically figures out that, okay, first it needs to go pull a web page using something like wget and pipe the result to grep and then look for the word that the user is asking it to look for. Or more complicated, like for example, I was a founder of a company called robin.io, which was basically cloud native platform where you could deploy really complex storage and network intensive application. In that cluster, let's say you would like to deploy something by saying, hey, could you deploy an app from the template named postgres-ha, name it mydb, and by the way, deploy it in the blogs resource pool. Also, if there's a failure, don't move the database to another node. So there's a bunch of actions that you want the Robin cluster to take. And you want the neural network architecture to take something like this and convert it to a command that looks like this. Robin app create mydb from the template postgres-ha in the resource pool blogs and then disable the auto relocate. And once it's deployed, you might want to do things like, hey, please back up my mydb app every Sunday at 7:15 and keep only the last 4 backup copies. Now, you don't really want the DevOps engineer to remember all the nuances of how to structure the backup schedule and what command line arguments to use. So you want a neural network architecture to do that. Just one more example for those who are familiar with Kubernetes. Instead of actually typing in all the kubectl commands, you might want to say things like, hey, can you deploy a web server using the image Apache version 2.4 and name it my site and then export it as a service on port 8080? We know that in order to do this, you might want to essentially run 2 commands. So you would essentially run kubectl create deployment, and then you would also run things like kubectl expose deployment as a service. You can get more sophisticated. For example, if you are a telco operator, and you might basically say something like, hey, there seems to be a congestion in the sites serving San Francisco area, and the KPIs are not looking good. Please increase the subscriber manager instance in this particular pod in that area. And then the neural network architecture takes this because it's trained on this, and then it will emit a bunch of commands, one or more commands or an API calls to take that action. This is the world that we are going to be going into. CLIs are great, but CLIs overwhelming because when the task is complicated, there are too many options and you really need to figure out what options to invoke, what arguments to pass, and so on. Instead, we should let the user express their intent as a conversation and then train a neural network architecture that will automatically emit out the corresponding commands from that. So that is another way in which you can look at sequence to sequence models. It's not just translating from one human language to another human language. It's from translating from any language to any other language. Human to machine, or machine to human. Okay. So now let's dive in and see how you would build such a neural network. So this kind of a neural network architecture is called as a sequence to sequence model. Why? Because you're converting something from one sequence to another sequence. English to a command or English to some other human language. Okay. They are also called encoder decoder models. So this was invented by Ilya Sutskever and team while they were still at Google in 2014. And this has been a game changer in the world of deep learning, where you could essentially use neural networks to figure out how to translate input into a completely different output. Now, what is the general idea behind seek-to-seek models? Let's get that understanding first, and then we can go and understand the architecture itself. So the general architecture is the following. Let's say you're given an input, and the input, let's say, is text. Let's say some things like, he drinks tea. So the first thing we want to do is you want to feed this input into a neural network. That neural network is called as an encoder. So what the encoder does is it tries to understand the context that is flowing across the individual words in that sequence or that sentence. And then it generates a context vector. I think the easiest way to understand a context vector is if there is a way in which you can get the essence of what that sentence is saying into a matrix, then that matrix will be a numeric representation of that textual information. Okay. So you would use a neural network architecture not to predict the next word, but to essentially extract the essence of what is being said in that sentence into this numeric format. Now, once you have this numeric format, you can then feed it into a different neural network, an independent neural network, which we can call as a decoder. And the job of a decoder is to basically take this essence from the source sentence and then translate or convert that into a completely different target sentence. And the target sentence could be another human language, or it could be some machine understandable command line, or it could be SQL statements, or whatever it is. Correct? So the general idea here is that the source is basically a sentence in one language, human or machine, goes through an encoder. The encoder essentially extracts the context and then passes it to the decoder. The decoder then emits out the sentence in a completely different language. The length of the target and the source could be completely different. So this is great, but how do you train the decoder to essentially emit this language out? Of course, you also need to understand how do you train the encoder so that it can extract the essence of the source sentence. We will see that shortly. But just to kind of do a very quick high level overview of how the decoder figures out how to translate it into a different language, essentially you start with the same model. You essentially feed in the input into the encoder, which extracts the essence, and you pass it to the decoder. Now, the decoder actually during training takes both the context, which is the essence of the source, and it also takes the corresponding sentence in the target language. Like, for example, if you're trying to build a sequence to sequence model to translate from English to Hindi, you would essentially pass he drinks tea, which is the source sentence in English, and you would also pass the corresponding ground truth value of this in the target language, which is Hindi, which translates into wo chai pita hai. Okay. So you would pass to the decoder both the ground truth value, which is wo chai pita hai, which is the corresponding sentence in Hindi, as well as the context, and then the decoder will emit out the corresponding target sentence. And you would essentially, of course, do the back propagation to ensure that both the decoder and encoder fix their weight so that you will make the correct predictions during inference. So this is the general idea behind sequence to sequence models. Okay. So what is the encoder and what is the decoder? Because they are two independent neural networks. And by the way, as you can see, instead of just studying one neural network, we are saying you can actually take multiple independent neural network architectures. In this case, it's two, and you can connect them together to form a bigger neural network to solve interesting problems. Correct? Okay. So this in the individual the neural network for the encoder and decoders are recurrent neural networks. Typically, it's a LSTM variant of a recurrent neural network because LSTMs can actually capture long-term context as well. Okay. So you essentially use LSTM as the underlying neural networks for these individual encoder and decoder neural networks. Now let's try to do a very, very quick recap of LSTM. I've actually covered this in a lot of depth in the prior episode, but I'll do a very quick recap. LSTM is basically something where you would take a sentence and you would break it into its constituent words. Let's say you call it x1, x2, x3, and x2, xn. And you would pass it through this LSTM, the same neural network. Each token gets in. And when it gets in, you would essentially pass it what they call as a long-term memory, also called as a cell state, denoted as C. And you would also pass a short-term memory, which is denoted as H. So a combination of the input, let's say you're starting processing the sentence, so the very first word, and the combination of that with the cell state and the edge state, which are initialized to 0, will make the neural network emit out an updated cell state, which is it's updating its long-term memory, and an updated short-term memory, which is H. And then to that, you would pass as the second input in your training sentence. And then the combination of the second input with the updated cell state and the updated hidden state will give you an updated cell state and hidden state, and so on. And all along, of course, the LSTM also produces individual outputs. The prediction for if you're given the first word, what could be the second word, it will predict that. If you're given the second word, what could be the third word, it will give it that, and all that. But typically, if you're interested only in what comes out at the end, you only focus on the prediction that comes out at the after you send in the last token of your sentence into an LSTM. And of course, the C and L can be seen as long-term memory, which is capturing all the important information. There are gates called forget gate and input gate that regulate how unimportant information is taken out from your long-term memory. The input gate ensures that important information gets added, and the output gate essentially ensures that it flows the context that is flowing across the individual words in the sentence from the beginning of the sentence to the end of the sentence. So this is the general idea behind LSTMs. If you do not really understand what the C, H, and all these gates really do or what it means, I would highly recommend that you go back and watch the prior episode, because I go into a lot of intuition. In fact, I use Breaking Bad, the TV series Breaking Bad, as an example to walk you through how an LSTM really functions. And it is critical to understand that to really understand sequence to sequence models. So now, assuming that you actually understand LSTMs, let's dive into the sequence to sequence models. All right. So let's start with how do you train a sequence to sequence neural network architecture? Okay. So we'll use the following example. We'll use the source language as English. So the training sentence first is he drinks tea. And we'll use the target language as Hindi. So because you're training, you have to give it what would be the corresponding Hindi sentence for he drinks tea in English. And that would be wo chai pita hai. Okay. So the first thing is you have to pass the source, which is English, into an encoder. And we said the encoder is an LSTM, right? And you also need to have a corresponding decoder, which is a completely independent, different LSTM, which we call as a decoder. And both of them are essentially LSTMs. Also, there has to be a way in which you can connect the encoder and the decoder. The connection is through what is called as a context vector, but it's nothing but you essentially extract the essence of the English sentence, which is the source, and then pass it to the decoder so that it can go and start to learn how to do the translation. Okay. Now let's walk through this step by step to see how you train the encoder and the decoder. So the first is you would pass the source sentence, which is in English, which is tokenized already, he drinks tea. And then you would pass it the LSTM that is basically the implementation of the encoder. Let's say we call it English LSTM. And then you also pass it the LSTM requires the long-term memory, which is C state, and the short-term memory, which is S state. You're basically saying I'm beginning a sentence, so basically it's going to be nothing. So I'm going to pass it 0 and 0, initialize it to 0 and 0. So you would pass it through this thing called LSTM forward. Now it goes in here, it sets the C state and H state and initializes it to what you pass in. You passed in 0 and 0, so essentially you're starting from scratch. C long-term memory is initialized to 0. H short-term memory is also initialized to 0. Now the LSTM sits in a loop, right? And it basically picks up every token in the sentence. So the sentence basically has he drinks tea. It picks up the first word, he. Now neural networks do not understand text, so it has to convert it into a numeric representation. It uses embeddings for that. So it takes a textual sentence and it converts it into a numeric representation, which is X. Now, we studied this in LSTM that the way you process this is basically you concatenate the numeric representation, which is the embedding for the word, with the short-term memory initialized to 0. And then you pass it through the three gates, forget, input, and output. And using that, you would basically say, I'm going to update the long-term memory by forgetting unimportant information from it and also adding important information to it, right? So that's how I update my long-term memory. And then I take the updated long-term memory and then I pass that through another function. And then I would use the output function to regulate the information that is flowing through my short-term memory. Remember that the short-term memory connects the context that is flowing across the words in your sentence, correct? So this is your standard LSTM, which you have covered in the prior episodes. I'll not go into the details of how the forget input and output gate actually operate, because I've gone into a lot of details in the prior episode. Anyway, so it is process he, and what does the processing of the first token do? It essentially produces three things. Number one, it produces the updated C, which I'm calling C1 in this picture. It produces the updated H, which is the short-term memory, which I'm calling H1. It started as H0, it became H1. And then it also makes a prediction. Neural network is supposed to make a prediction, right? It makes a prediction. Now, clearly, in an encoder, you're not really interested in what it's predicting as the next word. Because what you're trying to use the encoder for is to extract the meaning or the essence of what is the sentence is really saying in this context matrix, right? So I don't really care for the prediction. So while I'm showing that I'm capturing it here, notice that when I return back, I ignore all the predictions, okay? In the encoder, that is. Anyway, so you process the first word, which is he. Then you go back and look, is there another word in the sentence? Yes, there is. It is drinks. So I go in, extract drinks and extract the embedding for that. And then again send it back through the LSTM layer again. And then it makes an update for the long-term memory, which is C. You can see here. C1 becomes C2, H1 becomes H2, and it makes another prediction Y2, which again we'll ignore. Although I'm showing that I'm capturing it here. When it's returned, it's ignored. Then you go back into the loop and pick up the next word, which is T. You pass it through the LSTM again. It makes an update to C, its long-term memory, and then the short-term memory, which is H, and it makes a prediction. And then it goes back and checks if is there another word in the sentence? There isn't. So it comes out. And then it returns the predictions it has made. It returns the updated long-term memory, which is C. The last, so this is the last updated long-term memory, correct? And it also returns the last updated short-term memory, which is H. That's what it returns back. And you capture that as I said, you ignore the predictions in the encoder because you're not using it to make next token prediction. Although you ignore that, you save the long-term memory, which is called C state. I'm calling it encoder C state. And also the short-term memory, which is H state, the encoder H state. Because the short-term memory connects the context flow that is happening across the different words in the sentence. Okay. So all you have done right now is run a sentence through an LSTM and just capture short-term and the long-term memory. Now that becomes the context. There's nothing new here, right? Because we know that H, which is influenced by C, actually captures the context flow between the words in the sentence and the order in which these words appear in the sentence. So now we have a context. You have processed the source sentence through an encoder, and now you also have extracted the essence, and we call it a context. Now you have to pass that through into the decoder, right? Now, how does a decoder work? What the decoder does is a few interesting things. First is you need to, because you're training, you have to give it what would be the corresponding sentence in the target language, which is Hindi, for the source one. So source was he drinks tea in English. The corresponding sentence in Hindi, hai, which is 4 tokens, correct? Now, a few things, right? You need to essentially pass in, of course, you have to initialize the short-term memory and the long-term memory. And I am saying that because the encoder has already processed the source sentence, I can actually seed the decoder with the last outputted long-term memory, which is the C state of the encoder. And I can seed the decoder's H state with the last updated short-term memory, which is the encoder H state. Okay. Remember, in the encoder, you're passing 0 and 0, initializing it to 0 and 0. But in the decoder, you would essentially pass the encoder C state, last C state, and the encoder's H state. Okay, so that's what you're passing to the decoder LSTM. So what is the token that you pass to this LSTM? Do you pass wo, because that is a corresponding first word for in the target sentence? Actually, you don't. You pass a special token, which we call as start, which means that when you're passing the target sentence to a decoder, you actually have to take the decoder's target sentence from a training sample and you have to prefix it with another special token called start. We'll see shortly why. So you're going to prefix it. So this 1, 2, 3, 4 tokens in the target, you add another one at the beginning. So it becomes 5. So 1, start is the first one, wo is the second one, cha is the third one, pita is the fourth one, and hai is the fifth one. You also say the predicted thing will be the same set of sentence words in the target, which is wo chai pita hai, with another special token called end. Okay. We'll see shortly why we do that, but let's just go through this flow. So what you do to the decoder is the very first thing that you pass is a special start token, and you pass the encoder's last C state and the encoder's last H state. Now in this picture, I'm denoting it using not C and H, which is the traditional way in which you would denote an LSTM, but I'm calling it M and S. The only reason I'm doing that is because that way you can distinguish between the cell state and hidden state between the encoder and the decoder. Encoder, we are going to use the nomenclature of C and H. Decoder, we are going to use the nomenclature of M and S. All right, now you pass it start and the M and S values. Now, this is supposed to emit just like on the encoder, it's going through an LSTM, right? It is going to update its M state, right? And it's going to update its S state, which is fine. But it is supposed to make a prediction. Now, this prediction you don't throw away because now you have to check if the decoder is learning correctly or not, correct? So what you do is that you project it into a Y matrix and you send it through a softmax layer and it makes a prediction called coffee. What should it have predicted? It should have predicted wo, correct? But when you're given the start and the M and S, it predicts coffee. Now, clearly, the decoder's prediction is off, right? And how do you measure how off it is? You would use the cross entropy loss function. You would pass what should it have predicted and what is it predicting. The difference between the two, using a cross entropy loss, you'll know what is that loss. Now, the question here is, why are we passing start and why are we not passing wo? The reason you do that is because when you're using this neural network during inference, you obviously do not have the target's word, right? What the word that is going to be coming out. So you have to essentially have a mechanism by which you can trigger the decoder when you're doing inference to basically start emitting the first word in the target language's sentence just by taking this trigger word, which we call as start, and taking the encoder's last C state and H state, right? Because if you had wo, then that when you're inferring, you also have the first word of the target language, which you don't have, right? So you really need to have a trigger word. That is why you essentially start the input into the decoder with this special trigger word. Start. It can be anything. Typically, people use start or they use something called SOS, which starts for start of sentence and so on. That's why you have start. Okay, now when you say start, it is supposed to predict wo, but it predicted coffee. So there is a loss, you capture that loss. Okay, now what you do is you have to pass this back, right? After start, what is the input, right? This is the input you're passing. What is going into the LSTM? It goes the second sentence. You go back in the loop, right? You pick up the second sentence. Now you have a dilemma. Now the dilemma is, do you pass what it predicted, what the prior run of the LSTM predicted, which is coffee, or do you pass wo, which is there in your training sample? Now, if you pass it coffee, then you can essentially make the LSTM learn better, right? Actually, what you do is you actually pass what is there in your training sample, wo. This is a technique in deep learning called teacher forcing. Now, you could actually pass coffee also into this. But it would take the neural network a lot more iterations to kind of converge so that the loss goes down because you're passing it the wrong next word. So the analogy for this would be something like this. Let's say you're going on a hike in the wilderness and this is the first time you're going to that place. And along with you is a guide, right? The guide has been through the trail before. Now you reached a fork in a road and you see two paths. Either you go left or you go right. Okay. And the guide asks you, which path will you take? And let's say you say, I'm going to take left. But the guide has already been through that trail and he has a choice. He can say, okay, I know that going left would actually be the wrong thing, but I could let this person go and explore. So eventually he'll take a left and he'll keep on going. And eventually he'll find out that, hey, what? I'm not reaching the end of the trail. So maybe I need to backtrack and go back to this fork again and then take the right side, which is going to the right. And then I would go that on that path. So the guide has two choices. Either you let this person go take the wrong path and eventually figure out and come back to the right path, or I can cut down the time of reaching the end by actually forcing me to take the right path, correct? That is what teacher forcing is. So what you do is what the right path is. The guide here is the target sentence in your training sample. So you know that the right path is wo. So you would essentially feed it instead of the prediction from the prior step. Okay. So you pass it, this teacher forcing. So now you pass it wo, you go through the same things and you go and update your M state and S state again, which is again the updated cell state and the hidden state. And then you make the next prediction. You send the prediction through the softmax layer, and let's say it predicts may. What is the correct prediction? It actually should be chai. If you're given wo, the next token is supposed to be chai, but it predicted may, which is fine because you started the neural network with random weights initially, right? And you really want those weights. The weights here are WF, WA, W, O, WY and all that, and the biases are BF, BA, BO, and BY, and so on. Initially, we randomize it, so it's making the wrong prediction, which is fine because what we do is it is supposed to predict chai. You can see here in this first time step. The first time step is token 2, that is. It's predicting May. So you do a cross entropy loss and say, oh, I'm supposed to predict chai, but you predicted May. I'm going to get a loss of, I'm going to calculate the loss, right? And then you go back and then you pick up the next, you need to feed the word into the LSTM again because the sentence is not done yet. Again, do you pass May or do you pass what is supposed to be the correct one, which is chai? We know that teacher forcing tells us that passing chai would make the neural network learn fast. So let's pass chai. Okay, so you pass chai and then it makes another prediction, which is, let's say, namak. It's supposed to predict pita, but it's predicting namak, which is fine. You do a cross entropy to figure out the loss between what it has predicted, which is namak, and what should have predicted, which is pita. And then you pass it again to the next, you pass it back into the neural network again because you're not done with the target's words, right? So then you pass pita and then it makes another prediction, which is mat. Then you pass that next token here, which is hey, which is your last token in your training sample, and it is supposed to predict end. Because why should it predict end? The reason it should predict end is because as you see, when I'm training, I take for the target, I split the target into two things. As the input, I basically take all the tokens from the target sentence, but I prefix it with this special trigger word called start, and I need to compare it with something. So what I do is for the target, I suffix it with this trigger word called end. So I know I can tell my neural network that your prediction starts with a special trigger called start, trigger word, and I know that you are done because this is needed during inference, that you're done with your sentence. I know that you've reached the end of a sentence when you give me a trigger word called end, right? The special trigger word called end. So I need to tell the neural network that, hey, not emit this special trigger word, that during inference, I know that I need to stop and say, okay, my sentence is fully formed now. Okay. You pass the last word, which is hey, into this neural network, and it's supposed to predict the trigger word end because you're ending the sentence. It predicted Dalo, which is fine. So for the source sentence, he drinks tea in English, you wanted the neural network to learn that the corresponding Hindi in the target sentence would be wo chai peeta hai. What the neural network predicted is a completely different thing. Coffee may, which actually in English translates to do not put salt in coffee. Okay, it's wrong. And we know it is wrong because initially all the weights are randomized, right? Now you want to basically fix these weights. How do you do that? You basically take an average of all these losses for this sentence. Now you have a final loss and then you adjust the weights. How do you adjust the weights? I told you in the last episode that in the LSTM neural network, the way you adjust the weight is you pass the loss here. If I calculate the gradients, you adjust all the weight matrices here with that loss. And then you would essentially back propagate in time because if you look at it, an LSTM basically unrolls and runs the same, it runs all the words of a sentence again and again in a loop. So what you have to do is that you essentially adjust the weight once here, go back, 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 adjust the weight once here. So now you have gone through the decoder completely. However, the decoder is starting to make predictions from what came from the encoder. So what you have to do is you have to jump into the encoder, adjust the weights in the encoder here, jump into the previous incarnation or previous invocation of the LSTM, adjust the weight here, and jump back again and adjust the weight here. So you're doing back propagation in time, first starting at the decoder and then going back and then going into the encoder and then back propagating in time and adjusting the weights there. Now you do this from across thousands and tens and thousands of different combinations of English and Hindi training sets, adjust the loss, and over time you will notice that the LSTM basically adjusts its words accordingly so it can start to make the correct predictions. So given a source sentence in English and a trigger word called start, it will start to make the predictions correctly, which is how you infer, right? So let's actually quickly go through the inference ones. In the inference, you're only given the source sentence, which is he drinks tea in English, and you want your now trained neural network to make a prediction in the target language, right? The target language is Hindi. So the way you do that is you take the same encoder, you take the same decoder, okay? So the source is basically he drinks tea in English, and you pass it through the convert routine, which is going to make the predictions. It takes the source language, English. So you pass it the encoder, which is English LSTM. You also pass it the decoder, which is Hindi LSTM. Okay, so this goes in there. Now you pass the English sentence through the encoder, like we saw in the training, right? It's exactly the same thing that you do during training. You do that during inference for the encoder. Okay, you pass the English sentence and so on. Only thing that during inference you never adjust weights. That's all. Okay, but you essentially pass the English sentence to your encoder. And what do you collect? You collect the essence of that sentence. Correct? The essence is captured in the encoder's final C state, right, which is C3, and the encoder's final H state, which is H3. Now that becomes the thing that you would use to pass to the decoder's LSTM, right? So as you can see in the decoder, I'm passing M and S as the last state that is coming from the C state that's coming from the encoder, the last state that's coming from the decoder H state. Okay. Now you do not know what is going to be the corresponding first word that the sequence to sequence model is supposed to predict for the target language. So what do? You have to give it the trigger word start. Why? Because you train the neural network, you train the decoder that if you see this trigger word called and you see this and the prior C state and M state from the encoder, I want you now you predict the first word that should come out in the target language. Okay, so you would pass the trigger word, one token you pass, you send it to the same LSTM logic again of the decoder. You make the prediction, you softmax it, and then you get the, of course, the updated M and S value, but you also get the prediction, which is because it's already trained neural network, it's going to produce both. Now you have the first word. Is it the special end trigger word so that it can tell the decoder to stop predicting? It is not. It is wo, right? So I need to go back. And when I go back, I pass what? What do I pass into this decoder again? I basically pass this wo into the LSTM again, the decoder's LSTM again, so that it can make the next prediction, which is chai. Then I pass chai into this. Then I pass whatever it predicts, pita, which I pass it back into this LSTM again. Then it passes, it predicts hey. Then I pass hey, and then it predicts end, which is the trigger word that I get, so I can break out of my loop. And now I have basically predicted the all the tokens that correspond to this English sentence called he drinks tea in my target language called Hindi. So this way, I can take the source of any length, which is 3 words here, and I have predicted the target in a different set number of things, right, if needed. So wo chai pita has 4 words, correct? That's what I've done. Neural networks are not 100% always correct, right? I mean, you get to very close to correctness, but that's a probability thing. So sometimes you can get it wrong. So which means that sometimes you might have a runoff where for some reason it's not trailed well and it's not able to emit the end trigger word. So what do? You essentially add some protection by saying, hey, listen, what if you're sitting in a loop just predicting random words after that, you just bail out. Okay. So you would essentially pass and say, okay, the maximum number of tokens that I will after which I'm going to bail out is 20 or whatever that number is, you can pass that and then you can bail out. So there are 2 ways to bail out. One is you're seeing the trigger word called end, which the neural network predicted. The other one is you cap it to a maximum number of words that you're allowing it to predict. Okay. So this completes how a sequence to sequence model basically both trains as well as infers. Okay. So few takeaways here are you have now looked at a novel type of a use case for neural networks, which is you take 2 independent neural networks, you connect them together through this plumbing called as a context. The encoder, which is this part here, is the exact same thing during the training as well as the inference. The decoder is also the exact same thing. So basically you're using the exact same embedding layer, the exact same weights, all of that remains the same. The only difference between the training time decoder and the inference time decoder is during training, you basically pass the start trigger as well as the actual words in the target language, because that is what you have during training. The only difference between that during training and inferencing is in the inferencing you do not have the words from the target language, so you just pass the trigger word and the inferencing thing will go through the trained weights of the decoder's LSTM and make the prediction. Okay, so this is how sequence to sequence models are trained and then you would use for inferencing to make the prediction. Now, while this is a very powerful architecture, there is one limitation in this model, and let's try to understand that. So let's say I want to reverse this now. Okay, I'm going to give it an Hindi sentence and I want to train a neural network so it can predict the corresponding English translation for that sentence. Okay, now the sentence here is basically something like this. It basically says bhi akela, got 7 words in Hindi, which is the source, and in target English, it basically translates into 5 words. Never leave your luggage unattended. Okay, so how would this work? The encoder will basically take an apna, which is the first word in the source sentence, which is Hindi, and then it'll take the second word saman, kabhi, bhi, akela, na chhodna. It'll pass all that stuff. It extracts the essence, which is basically the last C state and the last H state of the encoder. Now it's going to pass it through pass that to the decoder. You start the decoder with a trigger word called start, and you end it with a trigger word called end. We have seen this already. Now observe a few things here. The first thing here is, if you look at the decoder, okay, when it is predicting the first word, which is never, this never actually is corresponding words in the source is basically kabhi bhi in Hindi. Okay, leave is basically 2 words. Your is corresponding is only a single word called apna. Luggage corresponding word is saman in Hindi, which is again 1 word. Unattended is akele. Okay, so the key observation here is the following. First is, of course, the lengths do not match, which is fine, that's what the sequence to sequence models help us do. But the first interesting observation is that the ordering is different. The first word in the target language in English is not the first word in the source language, right? It is basically the third word. So the orderings can be completely different between the source and target language. The second observation is, like for example, leave or even never, they do not map to one word in the source. So leave and never are words in the target language. They map to more than one word in the source. And there are some words in the target, like your and luggage and unattended, they map to only a single word in the target. Correct? So there is not a one-to-one mapping between the target and the source. The other thing is, we are basically saying that the context vector, which is capturing the essence of the source, you're only deriving it from the last cell state and the last H state. Can you really take a very long sentence and cram so much of information, so much of context just in one matrix? And that's a question that 2 other gentlemen asked. One is called Bandanov, the other one is called Luang. And they basically said, okay, for longer sentences, just using the encoder's last C state and H state does not work because it really cannot capture the essence of long sentences in one matrix. The other observation they made is, like I said, right, the words do not have one-to-one mapping. So some words need to focus on one or more words in the source language, and the ordering could be different and all that. So it was Bandano in 2014, after he saw the sequence to sequence paper that Ilya Sutskever published, he introduced this concept called attention. And then Luang in 2015 improved upon Bandanov's idea of attention mechanism. This is considered to be a landmark event in the world of natural language processing. An attention mechanism is considered to be one of the most influential ideas in the last decade of deep learning because it is the one that gave birth to large language models. I mean, in fact, Vaswani's paper, which came out in 2017, which introduced the world to the transformer architecture, the paper itself is titled Attention is All You Need. So it is that much of a watershed moment in the world of deep learning and AI. Okay. The idea is very simple, but the fact that it had to be invented for machines to really understand human language is a remarkable thing. So now let's try to understand what is it that Bandano or Luang have invented. I will save the attention mechanism, the ideas that Vaswani and his team built in Transformers for season 3. In today's episode, I'll actually focus on the optimization that Luang proposed to the Bandano attention, because later part of today's presentation, I'm going to give you a demo and I'll actually implement the Luang. So I'll actually focus on that. Even in production use cases, people tend to use Luang because it performs better than Bandanos. Although Bandano was the original inventor of the idea. Okay, so what is attention? So let's try to get into what attention is and how do you calculate it and how do you essentially enhance our sequence to sequence model to leverage attention mechanism. Okay, let's go back to this example of translating from Hindi to English. So you're taking the source sentence in Hindi and translating it into the target language, English. Never leave your luggage unattended. Now, if you were to basically take these words, okay, as humans first, just to kind of get an understanding of this concept, and you were to put it into a matrix like this, a table like this, the The rows are basically the words in English, which is the target language. The columns are basically the words in the source language, which is Hindi. Okay, so the columns are apna, saman, kabhi bhi, akela na chhodna. There are 7 words in the source language, which you pass to the encoder. Rows are never leave your luggage unattended, which is 5 words, which is in English, which is the target language, which you pass to the decoder. So in this matrix, let's say you initialize everything to 0. Now you look at the first word, never. Again, it's not the machine, it's a human trying to do this. So in never, you'd basically say the first word never. Which of these words in the source language influence the word never? Which of these things? Or another way of putting it is, in the target language, the word never, what should it focus on? Which words in the source language should it focus on? Should it focus on apna? Should it focus on saman and so on? We know that the word never actually corresponds to kabhi bhi, maybe even na a little bit, right? In the source language. The word never, it'll draw signal strength from kabhi, 55% of the signal strength from kabhi and 45% of the signal strength from bhi. Go to the next word, leave. And you can say leave is basically 20% of the signal strength from na and 80% from the word chodna, right? And 0% from the other ones. Your 100% of it basically it focuses on the word apna and 0% on the other words, right? The luggage, saman, 100% on the word saman, right? And the rest is 0% unattended, 100% on the word akela. Okay. So what we have established here is there is a way in which, as a human, you can basically look at each word in your target and then figure out what words in the source am I going to make this word focus on to get the correct translation. Okay, this can be seen as an attention matrix. Why? Because you see that the target words are attending to some words in the source more than they are attending to the other words in the source. Okay, that is what is an attention matrix. Now, 3 questions that come up. One is, how does this improve prediction in the decoder? The second question is, how do you calculate these values? I'm showing you 45%, 55%, 100%, 20%, and so on. As a human, I'm assigning this thing because I know both these languages. How does the machine actually calculate these values? And the third one is, where do you stick this attention matrix in your neural network architecture? I told you that the decoder and the encoder are LSTM networks. There is no provision to throw in another matrix, which I'm calling attention to that. So how do I do that? So these are the 3 questions that come up. So now let's look at that. All right, let's understand the attention mechanism in sequence to sequence models. So this is the code for the encoder and this is the code for the decoder. We basically said that the encoder, you initialize it, the C and H state to 0. You pass it the source, the tokens in the source language, which is apna, saman, kabhi bhi, akela na chhodna in Hindi. And then you process it and then it emits the last C state and H state, which you capture here. The encoder's last C state and the last H state. You pass that to the decoder and the decoder processes this. We have already seen this, right? And in the decoder, you basically give it a special trigger word called start and the actual translation, and then it does this. Okay. The first question, where do we stick the attention matrix here? One thing is that we know it has to be on the decoder side because you're trying to make the decoder figure out which of the sources words that it needs to focus on, correct? So where do you put it here? Do you put it, for example, somewhere here where the M state is being updated? M state is the decoder's long-term memory. The decoder short-term memory is called S. Okay, that's a nomenclature that we are using. You put it here. Clearly, there's no easy way to put it here, but if you put it here, does it make sense? Actually, it doesn't, because if you look at it, what you're saying is, in order for the decoder to make a prediction of what the word should be, right? It's at the prediction stage, it needs to know which one does it focus on. When I'm predicting, you need to tell me what I need to focus on the source. The M and S is nothing but you're trying to build the context that is flowing across the words in the target sentence, correct? Here you're not focusing. Here the M and S only are trying to build the context flow within that language's sentence. What you really want to do is you want to influence the prediction based on that context flow. So this part here, which is basically the final prediction layer, which is where Y is going through the softmax, that seems to be the right place where you can stick the attention matrix. Okay, so fine. So you're going to put this attention layer over here. All right. Now, what is it that you have to pass into this thing? We already are passing the C state and H state. Okay, but we also said that for the decoder to focus on certain words, it needs to know what actually is there in the encoder, which is not adequately represented by only the last C state and the last H state of the encoder. You actually also need to know all the corresponding H1s, right? The H1, H2, H3, H4, H5, H6, and H7. All of them you need to know. That is the only way it can focus, right? Because it never has to focus 55% on Kabhi and 45% on V. It needs to know all this H1, H2, H3, H4, H5, H6. Correct? Now, so you can actually update your context not just with the large C and H values, but all the values that are there through every time step of your encoder. That is one observation that attention mechanism inventors made. So how do you modify this code so that you can get all the encoder's H values? Okay, encoders all the values are H1 through H7, correct? It's quite simple. The change that you make is you add another array or another variable called encoder all states. It's an empty array at the beginning. As you're going through the loop in your encoder, LSTM, processing each word, you basically also save the individual H values that you're updating, right? It starts with H0, initialized to 0. You update H1 here, you update H2 here, you keep on capturing that and then just return that. So in addition to emitting the last C state and the last H state, you also emit all the encoders all its previous H states. One question is, why not emit all the C states also? Why only the H states? The reason why only the H states is needed is because, remember, going back to our LSTM explanation in the prior episode, the H state is the one that is stitching the context that is flowing through all the words in your sequence or a sentence. The C state is basically, think about it like a whiteboard or a long-term memory that is capturing what is important and what is not important. It's basically a memory board where you're capturing that thing. The context flow actually is happening through the H. And by the way, the H itself is influenced by the value of C. Of course, C is also influenced by H. There's a dependency between the two, but H is the one, the way it flows, the output gate is the one that's capturing the context flow. So that is the reason why just the encoder's H state is adequate. Okay, all right. So now we know that in order to implement attention, encoder change is very trivial, just two lines of code, right? One is to initialize the encoder all states to 0 and then keep on appending it and of course return that back, right? Very, very, very trivial to improve the encoder. Now let's look at what do you do with the decoder. So this is the decoder code, okay? And we already established that the attention matrix should go over here. Over here is what? Basically what you're doing is at the prediction layer, Y, you're saying Y is predicted as whatever the decoder's short-term memory is. The decoder short-term memory, which we are denoting as S here, is the one that is stitching the context flow that is happening between the words of the decoder, correct? You're saying that context flow I'm passing to the final output projection matrix to make the prediction. So clearly we know that we have to do something with this S. So you have to replace this S with attention. If you can, you can enhance the traditional LSTM, right? So that instead of just passing S to make the prediction Y, projecting it to this Y, WY matrix to make the prediction of the token, if you can just enhance it with the attention matrix, then that you can influence the word that is coming out. Correct? So how do you make that S to S with attention? Okay, let's study that next. So the number of lines of code needed actually is just 4 lines. In 4 lines, you can accomplish everything. Actually, in deep learning, you'll notice that the actual implementation is very small, right? I mean, even the original Llama LLM implementation was just about a few hundreds of lines, less than 1,000 lines, and you can do such powerful things. I mean, implementing those 1,000 lines or so takes enormous amount of intellectual thinking and all that to get to the ideas. The actual implementation is less. Even here, attention is a landmark event, right? In the world of deep learning, when you're using it in the context of sequence to sequence models, I think in 4 lines you can actually accomplish that. But knowing how to produce these 4 lines is where the intellectual brilliance is, okay? Which is what we have to credit Bandano and Long for. Okay, so this is the matrix that you need to produce, okay? How do you produce this matrix? So the way you produce this matrix is the first word, right, in the target, never. You want to see how similar they are to the words in the source. How do you measure similarity between two matrices? Know that S and H and all these are matrices, right? So how do you figure out the similarity between two matrices? You do a dot product between them. So what you're doing is when the first word token comes in never, right? You say how similar is S1, let's say, is never to the other words in my source. The source is represented using this encoder all states H1 through H7. So you take S1, you do a dot product with H1, you do S2, do a dot product with H2, do S1, H3 and so on. essentially do this dot products. Then you go to the next word, you do the dot products again, S2 with H1, S2 with H2, S2 with H3, S2 with H4, and so on. You repeat this thing, right? So you're doing essentially a dot product, which is like a cosine similarity between two vectors. Now let's take a quick pause here. I think this is a remarkable thing that it actually works. Because what you're saying is, if you can convert words into their corresponding embeddings and make a matrix out of it, and there are two different languages and you have sentences in each of these languages, what this is telling you is, even though the words are different, they sound different and all that stuff, as they are stitched to form a sentence, and if the meanings of the sentence and the source and the target is the same, what you're saying is that you can actually establish similarity by just taking dot products, right? Other way of looking at it is, in two different languages that humans have invented, the words could be very different. As long as the meaning of those sentences are the same, there is a similar way in which the context flows between those words. I think that's a very, very phenomenal observation on which this whole attention thing is built when it comes to language translation. I mean, there are more brilliant things in attention that we'll study in season 3 when I teach you the transformer architecture. But when it comes to language translation, the similarity thing is pretty brilliant that way. However, notice a few things here. This formula by itself is not that great, because what you really need is, you need to basically figure out how much of this word in the target should I really focus on. It's not that I'm going to focus on it equally, right? How do I establish this? As a human, I'm putting out these percentages. How do you make a machine come up with these percentages, right? Or these weights? By throwing in a weight matrix. Instead of just doing S1 dot with H2, S1 with H2, and S1 with H3, or S3 with H3 and all that, you just throw in a weight matrices, okay? Individual weights. So this can be seen as a weight matrix, right? Because I do not know. I mean, the machine does not know what percentages it is. So you throw in a weight matrix, you initialize it all random. And with training, these weights will adjust so that it will extract the right percentages. Because if it is extracting the wrong percentages, so that the loss will never converge. And using the gradient descent algorithm, that the loss will start to converge to zero, because the gradient descent will adjust these weights in the right direction. Correct? So just with anything in deep learning, when you do not know what it is, you throw in a weight matrix and you make the neural network learn it as part of the forward propagation and the backward propagation. Okay. So what you do now is, you take the weight matrix and then you calculate this values like this, right? S1, W11, H1, and so on. You create this. Now you notice that that also goes through the softmax layer. These individual calculations goes through the softmax to actually create this attention matrix. Why is it going through softmax? The reason it's going through a softmax is because what you want is, okay, the weights are all whatever values, okay, some numbers. But you want to basically create what percentage of, let's say, this Kabhi do I want to capture? What percentage of B do I want to capture? So you want to basically, because you can only capture 100%, right, in totality. So you want to basically create a softmax across this entire row, so that I can basically say 0% of this, 0% of 0% of Apna, 0% of Saman, 55% of Kavi, 45% of B, 0% of Akele, 0% of Na, 0% of Chodna, right? That would be the way I want to capture the or focus, right? My never on these words in the source. What is the mathematical function that allows us to do that? Softmax. That's the reason why you do softmax. Once you send it through the softmax, all of this becomes like A11, A12, A13, and so on. So now all you've done so far is you have created an attention matrix. That's all you've done. You've created an attention matrix that tells you what words of the target focus on what words of the source. Okay. So all we have done so far is that we have constructed this attention matrix. But how do I now connect this attention matrix back into a neural network architecture? For that, what you do is you take this attention matrix and you concatenate it with the S values, right? The S0, S1, S2, S3, S4, and S5. That's what you see here. Okay. That way, what happens is that you can take not just originally it was just the S that you're passing. Now you're taking S and concatenated attention matrix. That becomes your input into the output layer here. Okay. The paper basically, this Luang attention, by the way, it actually talks about taking this as command and passing it through a TANH. I think the reason they want to do that is because you're calculating this attention matrix outside independently of everything else. And you want to make sure that the values are bounded. TANH gives you a bounding between -1 and 1. and that is the reason why you do this. But how much to actually swing it between -1 and 1, you do not know. So what is the answer to those kind of I do not know in deep learning? You throw in a weight matrix, and that's why they throw in another weight matrix, which I'm calling WP here, which will learn how much do you want to swing this values. Okay, so you pass that. So you're converted from S, the original implementation of this thing, to S with attention, and voila, now you essentially have figured out a way in which you can plug in attention into your sequence to sequence models, and you can dramatically improve the quality of conversions from one language to the other, because even if the sentences were longer in either of these languages or both of these languages, source and target, because of attention, it knows what are the right words. The target knows what are the decoder knows what are the right words in the source that the decoder needs to focus on to predict the words in the target language. Okay, so this is, as I said, it's a landmark event in the world of deep learning, and it came out in 2014, late 2014, and 2015 is when Luang optimized it like the way I showed you here. And just 2 years later, in 2017, this idea was further developed by Vaswani, and he published this paper called "Attention is All You Need." That is the importance of attention in the world of language models. Okay, so with this, now let's go and see how you can implement what I originally said, right? Conversational language interface, where I can take English sentences and train a neural network so that I can print out the corresponding Linux command so that you don't have to remember the command line syntax. Let's see the demo of that now. So before we get into the actual implementation, I'm going to give you an overview of the setup first. Okay. So the tool that we're going to be building is called Jarvis, and it's going to be doing conversational language interface. So where I'm going to give it, while training, a bunch of English language sentences, things like display files under this folder xcvz, and then I also give it a corresponding Linux command ls-l xcvz, and I would give tens and thousands of such samples, and I'm going to train my sequence to sequence neural network to learn this thing, that if I were to in the future, after training during inference, give it a sentence like this, it should emit this command. Okay, so for that I will need an encoder LSTM. So I have this encoder LSTM, and then to that I'm going to be passing display files under xcvez. Okay, that's what I'm going to pass. Now this encoder LSTM will process it, and it's going to generate all the encoding states H1 through H4, the intermediate states. It's also going to produce the last final C state and H state of the encoder. Now we also need a decoder. I'm calling this training decoder here. To the training decoder, I'm going to basically pass the last C state and H state from the encoder, and I also pass all the encoder states, the intermediate encoder states H1, H2, and H3. Okay. Now to the decoder, I'm going to be passing the Linux command, and I already told you that you need to start with a trigger word, and let's say the trigger word is called start. So with start, as well as the encoder states and the encoder's C state and the H state, it's going to produce ls. And then if I give it ls, it's going to produce -l. If I give it -l, it produces this. And if I give it this, it produces end. Okay. So this is the setup for the training. Now for inference, once it's trained, all the weights are set up. I'm going to give it just this English language sentence, display files under, and now we want our sequence to sequence model, which is a combination of encoder decoder, to produce the corresponding Linux command. Okay. So for that, what do? Number one, we use the encoder as is. Whatever we have used in the training, we're going to use the exact same encoder, which means all the same layers, all the same weights, everything. Obviously, we're going to use that because we have trained the encoder, correct? So to that, I'm going to pass the string that I'm giving during inference, display files under this folder called presentations. Now, what happens is that during inference, one change that we make is, while we use all the weights of the decoder and pretty much all the layers as is, obviously because you're trained the decoder, you're going to use it as is. We are going to make a copy of all those layers, those weights and all that. And what we do is we are going to give it one trigger word, because obviously you do not know what the command is. You have to give it a trigger word so that the inferencing decoder can make the prediction. So the key thing to understand here, right? During training, you essentially create an input layer to your decoder LSTM, which is equivalent to the maximum length of any given command that is there in your training. Correct? And during inference, you don't know how much you're going to be producing. So what you do is you essentially create an input layer that only has one token. Okay. So which with that one token, we just essentially start with the start trigger token, and then the encoders all the hidden states H1 through H4 and its last C state and H state. It is supposed to make a prediction and generate the first token in the output command, correct? So that's the only change you make to the sequence to sequence model between training and inferencing. All the weights are reused exactly the same way. Encoders, all the layers are exactly the same. Decoders, all the weights are exactly the same. The only change you make is during inference, you essentially change the input layer so that you can just give it one token, it'll predict the next token, and then once it makes the prediction of next token, you pass that token back along with the updated M and S, as well as all the encoder states, because that is needed during attention calculation. And it is going to produce the next token. Then you pass that back. So dash L you pass back, and then it produces XCVZ, and you pass that XCVZ back, and it produces end, which is the end token that tells you that the command is now complete. So this is what during inference the sequence to sequence model is going to produce. Now, look at the English sentence that we are given. Display files under presentations. But what is the decoder producing? It is producing this XCVEZ. But the reason it's doing that is because the decoder is trained on several placeholder names for all these variables that you're going to be using. And the decoder can only produce or generate tokens that it has seen in the vocabulary. And during training, you had essentially trained it with this one, ls-l-xcvz. That's why it produced that. That is why what you have to do is during inference, you essentially have to build a presentation layer. And all the presentation layer does is it figures out a technique by which it can replace these placeholders that the decoder is going to generate with the variables that are being passed in the prompt that you give, the English level prompt. So in the English level prompt, it says display files under this folder called presentations. So this XCVEZ is replaced with this variable called presentations. Okay, that's actually outside the neural network. This is basically a presentation layer that we need to build. Okay, so with this background, now let's jump into the code. So I've implemented a collab notebook, and in that collab notebook, I'm going to be implementing this conversational language interface, which essentially takes English and converts it into Linux commands. I'm going to call it Jarvis. And I start off with importing some Python modules. Let me run that. And then, by the way, just to kind of show you, let's start with the output. What I would actually be using is if I give it sentences like, hey, create me a folder named AI, the Jarvis translator, which is built on Seq2Seq, is going to give me this command called make dir AI, or I can say please rename the directory AI to AI presentations. It does mv AI to AI presentations. Copy file sequence to sequence.pptx to folder AI presentations. It emits this thing called cp seq2seq.pptx AI presentations. Kindly rename it from sequence to sequence.pptx to encoder decoder. So it does mv. So basically that's what we want it to do, correct? So now let's go and see how you would build something like this. So the first thing is that I need to train my neural network. Before I show you how I build the neural network, let me show you this helper routine that I wrote that will produce all the relevant English and corresponding Linux commands for that. And it's actually pretty simple. I basically generate a bunch of commands for creating directories. So essentially something like, hey, please create or make or build a or the directory or folder or whatever it is, and calling it or whatever, and then the name. So essentially it just produces a bunch of English level sentences and their corresponding Linux command. Similarly for delete, it will do that. For the rm command, that is For rename, it will do that. It's going to do it with MV command. For copy, it will do it with CP command, and so on. Okay. So this is our helper routine. Let me collapse this for now. You don't need to see that. Okay. Now let's look at this Jarvis translator. Okay. For that, let me show you side by side a diagram and the code so it becomes very clear. Okay, so what we do is in Jarvis translator, actually, before you get to the code, let me show you how you're going to use it. So I'm going to first generate some training sentences. So generate English to CLI. So let me run this. So it produced 56,500 English sentences. By the way, if you look at the sentences, the training data, it looks like this. So please copy or CP directory this to that. The command would be CP, please find pattern SNTI to this one. These are all placeholders, by the way. All these are placeholders. Okay. I generate the placeholders using a random function, which you can see here. Okay. This is what I use to generate the placeholders. Let's go back here. So this is about 56,500 such training samples I have generated. Okay. All right. Let me hit that. Okay. Now what you do is that to the Jarvis translator, and we'll see the implementation shortly. I'm going to parse this English sentences as well as a corresponding CLI commands. And by the way, all the placeholder values that I have generated, right, for these variables, I also bring that back because I need to substitute them later during inference, right? Um, so I pass the English sentences, the corresponding CLI commands for that, and all the variable names that I've used as part of training. That I send to prepare training data. And what the prepare training data does is that it's going to take these English sentences, it's going to tokenize all of them, and then it's going to do the same thing for the CLI commands, and it's going to give me sequences. Let's go and actually now look at this code. So first is, let's go here, prepare training data. You give it English sentences, you give it the CLI corresponding CLI commands and the placeholders. The first thing it'll do is it'll instantiate an English tokenizer, and then it's going to train the tokenizer on all the words that it sees in all my training English sentences. Okay. So it builds this vocabulary and all that here. And in that vocabulary building, for each unique word, it assigns a token ID, a unique token ID. The size of my English vocabulary is this, captured in English dash vocab dash size. Okay. Now I do the same thing for CLI. But for CLI, one thing that I need to do is remember that I need to have this trigger words called start and end. So in addition to all the CLI commands which are tokenized, right, I also give it the start and end special token so that when it is tokenizing it, it also assigns unique token IDs for the start and end with trigger tokens. Okay. So it's pretty straightforward. So basically, this will essentially generate the vocabulary for the CLI commands as well as it will tokenize it. Okay. Next thing is I basically convert these English sentences uh, after tokenization into sequences. So what does that mean? So if you remember in few episodes ago, I told you that in order to feed data into a neural network, you need to first convert everything into integers, right? Text to integers. And obviously what the neural networks wants to see is the word embedding, right? Which is a matrix for each individual token. So there is a special layer called embedding layer, which we'll show you shortly. You can pass at that. But what the embedding layer needs is what is the corresponding token ID for each of the text string that you're passing? Because neural networks only understand IDs. You pass it the token ID, and the embedding layer will look up that token ID, and then it will correspondingly generate an embedding and all that stuff. So you need to have something that will generate those sequences. So it's basically I'm capturing all the English language sequences into this. Okay. All right. Now I do the same thing for the CLI commands as well. But in the CLI commands, like for example, if it is display files under this directory, the command is of course ls dash that directory name. But remember that I need to train it with the trigger word called start. So I need to start with that. So I'm going to actually take the commands and I'm going to create two things. I'm going to create this thing called command in, and then I'm going to create this thing called command out. Command in is what? The input that I'm passing to the decoder LSTM, which starts with the start trigger word. and the tokens for the corresponding command as is. And command out is what? Basically the CLI commands tokens ending with this end trigger word. So I can basically know during inferencing that this is when I need to stop. Okay. And then once I have these things, I'm going to again create corresponding sequences out of the command CLI also. Okay. Now, we also know that you need to essentially have fixed size inputs going into your neural network. So what do you do? Because I mean, each English sentence could be of variable length. For example, display files under this folder is only 4 tokens. But if I say things like create directory foobar, that's only 3 tokens. So you cannot have variable size inputs going in because a neural network needs to have fixed size input going in. So how do you solve that problem? You solve that problem by selecting an input size of a fixed length. Let's say we call it max English length, which I'm passing as input here during instantiation of my Jarvis translator. Initialize that to 20. And I basically say for each training sentence that you're getting in, if you have tokens that are less than the max length, then essentially pad the remaining with a special pad token, which is essentially a token ID of 0. Okay. And also what happens is that if your incoming sentence is much longer than that, then you would essentially, it will also truncate it. That's also the thing. So you should choose your max English length or max sequence length very carefully. Now I need to also do that for the decoder inputs, and I need to do that for decoder outputs, which is this right here. Decoder inputs is here, decoder output is there. That's all I'm doing. So this is pretty straightforward stuff. And what I can do from the prepared training data is I will again tokenize and I will pass back the sequences for then which I can pass to the encoder, sequences which I can pass to the decoder as input, and the sequences that I'll be collecting from the decoder as output. That's all I'm doing. This is what prepared training data does. Okay. By this time, all the input training data has been tokenized and you have a vocabulary and all that stuff. Okay, let's run this. So let's run this. So I run this. What I get is basically a model. So first of all, I have all the English sequence lengths and all that, CLI sequence lengths. And by the way, I'm also calling jarvis.build model, and it builds this model, okay, which has 10.9 million parameters. So let's see what is this build model doing, okay. Now, build model is going to be building my sequence to sequence model. I'm building the training model, okay. Let's go and look at the training model. Where is this? It's here. Okay, so let's start with the encoder first. The encoder, this is what we are inspecting here. Okay, this is code. So the encoder, the first thing you need is an input layer. Correct? How many tokens can go into the input layer? Whatever you're defined as your max English length. So that's why I have an input layer called max English length. Now, from the input layer, you need to basically pass that inputs, whatever is going to come in, to an embedding layer. Because again, a neural network needs to get not the token IDs, it cannot work on token IDs, it actually works on the corresponding embedding for each of the token IDs. So you need to have an embedding layer. So I create in Keras, there is a special embedding layer. So I basically tell I'm going to link this input layer with the embedding layer. How is the linking happening? See, input encoder inputs equals input. So I pass that to the embedding. So essentially that linkage is happening this way. Okay. And what is the size of the embedding dimensions? I'm saying the embedding dimensions is this much, and which is passed as something. Then I instantiate the thing. It's actually 300 dimensions. Okay. That's what I'm passing. You can choose whatever number and experiment with it till you get good results. Okay. So from input, I have created an embedding layer. I have done that. And then now you need to pass what? Input to the embedding layer. Now you need to pass it to an LSTM layer. So I'm creating an LSTM layer with the latent dimensions, which is basically the size of your C and H matrices. I'm giving it as, if you're not getting instantiating it to 1024 as a default. Okay. So it essentially creates a C and H matrix, which is 1024 by 1024. That's what it means. To this LSTM Keras layer, when you say return sequences, what it means is, hey, don't just return me the last C and H values, return me all the intermediate H1, H2, H3, H4, and so on. That's what it says, which I'm going to be capturing in this variable called encode outputs. And return state means it'll return the last H and last C values. Okay. So this linkage here, input goes here, embedding goes here, and you get the LSTM. Okay. Now I can connect all of these things through this model utility or library function. And you say that the inputs is basically going to be the encoder inputs, which is this input thing, and the outputs is going to be what? I'm going to be outputting the encoding outputs, which is basically encoding states H1, H2, H3, so far, and the last H state and the C state. That's what it is. Okay. Now I capture that in the self.encoder variable. Now building a decoder is also something like similar. So what you do is the way you would build your decoder is pretty similar. You would again have an input layer. This time the input is going to be size what? Whatever is the maximum sequence length of your CLI commands. You pass it through embedding layer, same size that I'm giving for the embedding. You can choose different dimensions, but really don't have to. So I pass that, and then I create an LSTM. For the LSTM, I don't really care to see the last M4 and S4 values, right? So I can ignore that. But I need the decoder outputs, which is the S1, S2, S3. The reason I need that is because this attention layer needs to do a dot product between this S and the corresponding and the H1, H2, H3, H4s of the encoder. That's why I need this. I'm essentially telling my LSTM to output those things as well. Now I'm going to attach to this an attention layer. I'm using Luang attention. Okay. And then remember the attention matrix is created this way. Now, what you need to do before you give it to the presentation, the output layer is basically you need to concatenate all these S1, S2, S3s with the attention matrix. That's what I'm doing here. Concatenate and the decoder outputs, which is S1, S2, S3 and all that, with the attention output, which is calculated as this array here. Okay. Which I showed you basically how the attention is calculated using similarities. All right. Now what you do is that you have this attention weighted all these calculations of S hidden states of the decoder. You pass that to a dense layer, which is your projection layer, which essentially is again nothing but you take this and you project it into a large output layer, which is the size of your entire vocabulary. And once you have that, you can softmax that and you can figure out what is the token that it is going to pick, whichever the highest valued slot in that, the softmax is going to pick as the one. This is essentially logic calculation. Now you're going to tie everything together using Kira's model thing. So essentially you're saying input is encoder inputs here, encoder inputs here, and then decoder inputs here, sequence to sequence, right? And the output is going to be this logits, which is going to produce these tokens. That's all it is. And then I'm going to compile this model. I'm going to use the Adam optimizer and I'm going to use the sparse categorical cross entropy loss function. Okay. That is all I'm doing here. Before you go into the inferencing, I take it you understood how the training works. Okay. Now, by the way, you also notice that I'm giving it each layer, I'm giving it a name so that I can reference it back later during inferencing because I can go and say, hey, give me the embedding layer for this so I can rebuild that decoder that is needed to be rebuilt for inferencing. That's the only reason why I'm giving these names. All right, let's go back to this code and let's now train it. Okay. When you compile it, by the way, it shows that it has produced uh, an encoder decoder or a sequence to sequence model which has 10.9 million parameters and it's about 42 megabytes in size. It's a pretty small model. Now let's train it. Training is pretty simple. You say jarvis.train and then you give it all the English sequences, English language sequences, all the command CLI sequences which are in and all the command CLI sequences which are going to be out that side. I'm going to give it a batch size of 64 and I'll train it across 10 epochs. Okay, so let's run that now. So this is training. You see that the loss is going down, which is good. By the way, while it's training, let's just go back and see what this jarvis.train does. This jarvis.train, what it does is, okay, here it goes. If the training model is not built, actually it is built, but if it's not built, it'll build that like I just showed you. It's going to take the input and it's going to split the input into 80% of it it'll use for training and 20% of it it'll use for validation. And then it just calls the Keras.fit method and it passes this thing and then it just goes through the whole training, back propagation, all of that stuff happens there. Okay. So we see that actually it's pretty well trained. The loss is pretty low. The accuracy is pretty high, which is good. Okay, now our neural network is trained. So it's ready for inferencing. Okay. For inferencing, what I do is I'm going to give it some English sentences like this. Hey, create me a folder named AI and so on. And I have to pass it to jarvis.english to CLI, that English sentence. Obviously, you do not know what the command line is. The neural network needs to produce that from its weights and all that. So let's see the implementation of English to CLI. Let's go there. Okay. The English to CLI. What you do is the inferencing model built? You have not built that yet. So let's build that. Let's go and see what that does, which is this code here. Okay. So now let's look at this reference picture to see what happens here. Okay. I told you earlier that in a sequence to sequence model, the encoder is used exactly the way it is. So essentially, I'm using the same encoder, reusing the encoder. I'm not really building it. If you notice, I'm just saying training model dot get layer encoder embedding. I get that. I plug it back into this training model dot get layer encoder LSTM. So I'm essentially reusing the entire encoder as is. All the weights, all the layers, everything is as is. This input thing that you see here is, think about it like it's a neural network way of passing a variable into a function. Okay. Think about it like a conduit into which you can dump in data, input data or something. It really is not technically a layer that has weights. It's basically just a placeholder to hold your variables. I think that's the easiest way to kind of understand that. Okay, now for the decoder, we're going to use again, we're going to take the decoders, all the weights and all that stuff. But however, in the decoder, because you don't have the CLI command, you have to essentially give it a word called start, and then it starts to produce things one at a time. So which means that there's only one input you can give to the decoder, which is a trigger word called start. When it produces the output ls, you give that one input again back into the decoder, and it produces the next one token, and you give that same produced token back one token and produces another token, and so on. So which means that the input layer for the decoder is different than the input layer for the decoder during training. During inference, it is one token only. During training, it is basically the maximum number of CLI sequence length. That's what we showed earlier. Okay, so I'm going to create that, and I also need to pass the encoder's H and C values. I'm essentially having this, as I said, input is basically the easiest way to understand this is that it is a way in which you can pass variables to, just like you pass variables to a function. This is a way in which you can pass variables to a neural network, okay, in Keras. So in the decoder, again, I'm using decoder training model dot get layer embedding, so which means all the weights are reused. Training model dot get layer decoder LSTM, which means all the weights of the decoder LSTM are reused. And then to that, I pass the decoder's embedding. The initial states are this decoder H and the decoder C. I do that. Now I need to pass the attention. The attention is passed. I have to reuse the attention also because all the attention weights, the attention layer also had weight matrices. So for that, I have to reuse that. So I'm going to basically say get layer Luang attention, and essentially I plumb it all the way back. The encoder's outputs go into the attention as well as the decoder's S state. All this S states and the encoder's all its inputs, hidden inputs H1, H3 goes into the Luang attention. The weights are reused. I concatenated just like we see here. The S and the attention things are concatenated, and you would build the inference model of this. So it's a pretty straightforward thing. All you're doing is you're essentially reusing the encoder, you're reusing the decoder with the exception of just changing the input layer for the decoder. Okay. So the English to CLI command, coming back to this, will build the inferencing model. Then it will tokenize the incoming English sentence, and then it's going to pad it so that the remember the decoder, so the encoder basically was initially designed to take a maximum English length, which is 20 tokens or so. It's going to pad that, and then it will pass the English sentence to the encoder.predict. And what is the encoder.predict going to give you? It is going to give you all the encoder's hidden states, H1, H2, H3. It's going to give you the encoder's last H state and the last C state. Now to that, you're going to give the trigger word, which is start, okay, to the decoder. Okay, model.predict. you're going to give. Okay, model is what? The inferencing model. You're going to give it the, which essentially, if you go up, if you see up in the code here in the inference model building, it basically is building uh, the sequence to sequence connection. So you're essentially giving it the, what are you giving it? You are giving it the CLI sequence, which is basically the token ID. Okay. Then you're giving it the encoder's outputs, which is H1, H2, H3, which you calculated from here. And then you're also giving it the encoder's initial state. You're essentially seeding this decoder with encoder.h, the last h and the last c of the encoder. That's all you're doing. Okay. You make a prediction. Essentially, from that prediction, you figure out it goes to a softmax layer and all that. You use argmax to get the token ID of the predicted thing. From that token ID, you go to the CLI's vocabulary and say, give me the corresponding text string for that. You get token. And then you check, is that token that it produced end? If it is end, then you need to bail out of this thing because it has now completed the translation. If it is not, then you would basically save that token in this thing, decoded tokens, because that's what you're going to return back to the output, right, of this function. And then what do you do next? You need to pass this token ID that it generated back into the decoder. So essentially, you take the token ID that it predicted, right? The CLI sequence becomes that. It goes back in here. You pass that token ID. It produces the next token. Is it end? It is not. You append it to the tokens that are decoder tokens. Go back and do that. When do you end this loop? You either end this loop when you see this special end token, which it should produce when it has completed the thing, the command, or it's quite possible that in some cases, if it's not well trained, then it can have a run on and it will keep on producing some random tokens. So you can basically say, hey, what, stop producing it after a certain number of tokens. Anyway, so it's basically gathering all the tokens here. Okay. Once it is done gathering all the tokens, I need to now replace. Remember that it would actually produce something like this. If the incoming English sentence was display files under this placeholder XCVEZ, right, during training, it would actually produce ls-xcvez. Now, but during inference, I gave it grade display all the files under, let's say, presentations. I need to replace this xcvez um, with the variable that is passed in, the name of the directory that's passed in as part of the English sentence during inference, which is presentations. So I wrote a very simple code here. I'll not go into all the details, but essentially what I do is that I'm going to check if the tokens that it predicted are already part of the vocabulary, and I cross check that with the English sentence and I remove. Essentially, I will know that the incoming sentence that I'm giving as an input during inference does not have this XCVZ. So I need to replace that variable with this presentations. I mean, you can look at this collab notebook offline. I'm going to post the link to this in the comment section, and you'll be able to see this. It's a very trivial way in which you can do the placeholder replacements. You can essentially get very sophisticated and do many other things. I will talk about how to do these placeholder holder replacement in another episode. But for our purpose here, this suffices. So I'm going to do that replacement. Once I've done all that, I'm going to now join all these tokens together with a white space and return that back as the CLI command, right, for the English sentence that you give to input, right, to this English underscore CLI routine. So now let's run this. When you run it, you see that it's not this. Okay, when I run this, you see that for the English sentence, hey, create me a folder named AI. It outputs mkdir AI. Please rename the directory AI to AI-presentations, MV. It produces the command MV AI to AI-presentations. Display files under AI presentations. It does ls-l AI presentations, search for the word attention, and my report.pdf, it says grep.i. So pretty much it's producing the right corresponding CLIs for each of these English sentences. Okay. So now we conclude our demo of sequence to sequence models. So I wanted to just capture one thing before we end this episode. On the internet, there is several articles that say that there are different types of sequence to sequence models, things like one to one to many to one, and so on. Actually, I think that's all wrong because the name sequence to sequence essentially suggests that you have to give it a sequence and you're going to get another sequence back. So a sequence is essentially more than one inputs that you give it, and you're going to get more than one outputs, correct? Yes, obviously you can also give it one input and you can get many outputs, but you don't really need an encoder decoder kind of an architecture for something like that. Similarly, you don't give it a long sequence as input and you don't get one output, when you could use a traditional just an LSTM with an output layer that outputs one token out, correct? So I would basically caution anybody to actually look at sequence to sequence models that way. Sequence to sequence models are, you give it an input which has many tokens, and then it produces a corresponding set of tokens, more than one token in the target language. Okay, that is what sequence to sequence is. So very quick recap of what we have studied. So sequence to sequence model is basically a model in which you take two different independent LSTM networks, you join them together, you pass the first LSTM network, which you call it as an encoder, a sequence in the source language, and then that thing basically emits a context vector, and that context vector is passed to a decoder LSTM, which produces the sentence in the target language. Okay, that is what a sequence to sequence architecture is. And I also explained to you the concept of attention, which was invented for improving the translation accuracy of sequence to sequence models. Okay, so with this we pretty much conclude season 2. And in season 2 we studied many things. We studied tokenization techniques, where you can break long sentences into individual tokens. I explained to you how things like byte pair encoding works, things that GPT and Grok and Gemini and all these things use, right? Things like word piece tokenization and so on. I also explained to you what word embeddings is. I gave you an overview of recurrent neural networks. I went into the depths of why it's constructed that way, how does it work. I gave you a use case of when to use recurrent neural networks, both for processing text as well as for time series. And then I explained to you long short-term memory, which is an optimization of a classical RNN. I actually use the Breaking Bad TV series as a way to explain an extremely complicated technical concept called LSTM in episode 4 of season 2. And today's episode was sequence to sequence models. So with this, we conclude season 2 of our web series. In 2 weeks or so, I'll be starting season 3. In season 3, I'll be explaining the transformer architecture, as well as I'll be explaining large language models. I'll go through both the classical transformer architecture and large language models, all the way to the modern innovations that have happened all the way in 2025. Things like the latent attention, things like mixture of experts. I'll go through all of those things. I'll talk about reinforcement learning. How do you essentially improve the performance of an LLM, both in terms of performance as well as cost and so on. It's going to be pretty exciting, season 3. I hope you're looking forward to it as much as I am looking forward to actually presenting it to you guys. So until then, happy learning and thank you. And please do not forget to like, subscribe, and share this video, and subscribe to my YouTube channel, where I'll be publishing all these videos. Thank you very much.